electric field of electric dipole for a point on the equatorial plane. Now this is the figure as such. Now I am trying to draw it for you. Okay, say for example, this is the plus q charge, okay, and this is minus q charge, okay. This is the line joining the two charges. Now perpendicular bisector of line joining the two charges is the equatorial line. Now on this equatorial line we want to find out electric field somewhere here. So we place the test charge, that is plus 1 unit charge we are placing here. Okay, we place plus 1 unit charge here where we want to find out the electric field. Okay, now this is the point P where we want to find electric field. Now plus Q charge and plus 1 unit test charge will have the repulsive force. So this will be the direction of E, that is electric field due to plus Q, and this plus 1 coulomb charge or plus 1 unit charge will experience the attractive force by this. So this will be the direction of the electric field due to minus Q charge. Just I am extending it in this direction. Okay, so this is the vector. This vector is showing the electric field due to minus Q charge, and this shows the electric field due to plus Q charge. Now you want to find the resultant, so we draw the parallelogram. Okay, we complete the parallelogram just for the sake of understanding, that is not drawn in the figure which is okay. So we draw the parallelogram. Okay, so this is the parallelogram. Now this is the resultant vector of these two vectors. Okay, the first vector is this, second is this vector. So this is the resultant vector. Okay, so this electric field is due to minus Q charge. Okay, so this electric field due to minus Q, this electric field due to plus Q, and this is the resultant electric field because of the two charges which are that of the dipole. Okay, so this electric field is found to be in a horizontal direction from left to right. Now try to understand. The dipole moment is having direction from minus Q to plus Q. So that is from right to left. This is the direction of dipole moment P. Okay, and this electric field is in the opposite direction of the dipole moment. Okay, so if you want to show this electric field in terms of the direction of the dipole moment, then we can show it like this. Electric field E, that is in the opposite direction of dipole moment, so we multiply by unit vector of dipole moment P cap, but it is in the opposite direction, so we write minus E P cap. Okay, so electric field that is produced, resultant electric field which is produced is in the opposite direction of the dipole moment. That is why it can be shown like this. It is shown like this only, E. But if you want to show it in terms of the unit vector of the dipole moment, then minus E P cap you can show. Now this electric field is due to E plus Q and E minus Q. Okay, now we take say angle theta here. So this angle will be theta according to our geometrical understanding. Okay, because these two lines are parallel lines. Okay, this line and this line are parallel, and this becomes a transversal. So this angle, if this angle is theta, then this will also be theta. Now this angle will also be theta because this is the midpoint. Okay, this is the midpoint of the triangle. So these two angles will be same here. Okay, so now try to understand this. Here the alternate angle again, see, showing Z is made Z. Okay, so this angle will also be theta. So this is your theta, this angle will also be theta, as this is theta. Okay, because this is the point P, which is on the equatorial point. So the line joining P to Q and line joining P to minus Q, okay, that will make the same angle theta. Okay, so these are the two angles theta. So these two angles which I have shown here with this resultant electric field will also be theta. So this is a common understanding of geometry and electric field produced by these two charges of electric dipole. Now we proceed further. Okay. See, the magnitude of electric field due to two charges at plus q and minus q first of all is calculated. Okay. Now see, this distance we want to find. Now this is the point P, which is a midpoint. So this is A. This is the distance R. Okay, this distance is R. Okay, so this diagonal according to, rather hypotenuse according to Pythagoras theorem will become R square plus A square and square root of it. So that becomes R square plus A square. Okay, so this distance will become under root of R square okay, this distance will become R square plus A square. Similarly, this distance will also become R square plus A square with under root. Okay, this distance will also be R square plus A square. Okay, now we want to find out electric field due to plus q charge at this point P. So our general magnitude we want to write. So it becomes okay, kq upon square of distance. So k is 1 upon 4 pi epsilon 0 q, the charge which is there, that is positive charge. So we can write q upon 4 pi epsilon 0. Okay, k is our 1 upon 4 pi epsilon 0 q upon distance square. Now distance is r square plus a square and square root of it and square of it. Okay, so that will give you this equation. K is 1 upon 4 pi epsilon 0. So q upon 4 pi epsilon 0, 1 upon r square plus a square, and similarly the magnitude of electric field due to minus q charge will be this. So same magnitude of electric field is produced, but the directions are different. See, this is the direction of plus q charge, this is the direction of minus q charge. We have completed the parallelogram, and this is the direction of resultant electric field. Okay, now this angle is theta, so we take the component of E plus Q, and that will be E plus Q cos theta. Similarly, E minus Q, this also will be theta. So the component in this direction will be E minus Q cos theta. They both will be added. Okay, So we move further. See, just go through it. The direction of E plus Q and E minus Q are shown in the figure. Okay, the components normal to the dipole axis cancel away. Okay, so just these components, that is E plus Q sine theta and E minus Q sine theta, they will have same magnitude in opposite direction, so they will be cancelled out. Only this two component, that is E plus Q cos theta of this and E minus Q cos theta of this, they are in this direction and they will be added. Okay, so these two components are added, E plus Q cos theta and E minus Q cos theta are added because they are in left to right direction, that is same direction. Okay, so this is done here. Resultant electric field is found. Okay, both the components are added, so E plus Q cos theta plus E minus Q cos theta, both are added to find the resultant electric field. This is the magnitude. Try to understand. This is your magnitude of electric field. Now you want to mix the direction or you want to show the direction simultaneously. Then we put vector here. Then as I have shown that this direction of electric field is from left to right, which is in the opposite direction of the dipole moment. So we have to multiply this by minus P cap. Okay, that is why here minus sign is written. Okay, cos theta is taken common, so it becomes minus into bracket E plus Q plus E minus Q cos theta P cap. Okay, now write the values of these. Okay, just I am showing the simplification for the sake of your understanding. So this is the final answer. Okay, but some simplification. Minus is there, then E plus Q magnitude is 1 upon 4 pi epsilon 0 Q, so that will come out. Okay, so we take the common. First of all, the magnitude you want to write, minus is already there because of this P cap. Okay, because the direction of electric field in the opposite direction of dipole moment. So minus, then we take common, Q upon 4 pi epsilon 0. Okay, then we had 1 upon r square plus a square, but that will come twice, so this is multiplied by 2. Okay, so these values are written. Now cos theta. Okay, now try to understand this cos theta. Okay, if you want to find cos theta here, okay, this is the earlier simplification, just I am deleting, we will write it again. If you want to write cos theta, and cos theta is nothing but in this triangle, try to understand, this is the triangle in which you want to find the cos theta. So cos theta is adjacent, that is A, this value is A, upon adjacent upon hypotenuse, this we had found, and that is under root of r square plus a square. Okay, so a upon r square plus a square and square root of it, that will be the value of cos theta, and that will be understood with the help of the figure. Okay, so these are the things which are combined. Cos theta is written, or its value is written there in the next step. Okay, now see, we will go there. Okay, this is the simplification that we were doing. Okay, so here the magnitudes of both these electric field are same, so we write with negative sign because this is your vector value, or rather vector representation. Okay, q upon 4 pi epsilon 0 2 times, okay, r square plus a square, because both the values are same, so it becomes twice. Now cos theta is a upon under root of r square plus a square. Now if you rearrange it, then you will get this equation, that is minus 2a q upon this 4 pi epsilon 0. This is 1 power and this is half power, so it becomes 3 by 2. Okay, so it becomes r square plus a square raised to 3 by 2, and you want to show the direction also, which is in the direction opposite to the dipole moment, and that is why minus and this p cap. Okay, this is minus and p cap. Okay, so we are reaching at this particular equation. Okay, if you take a very large distance, so r is too much greater than a, special case. Okay, if r is too much greater than a, then neglecting this a, so you will have, okay, 2 qa upon 4 pi epsilon 0 r cube, because r square raised to 3 by 2, it becomes a is neglected. Okay, so it becomes r cube p cap with negative sign. Okay, now for the point on axis of electric dipole, electric field at very large distance is this. This we have derived yesterday or last lecture. Okay, and today we have derived this formula for the point on the equatorial point of electric dipole. The electric field at large distance is given by this formula. So these two equations we derived. Okay, now from these equations, that is derived in the last lecture and the derived today, okay, it is clear that the dipole field at large distance does not involve q and a separately. Try to understand, it is a product of q and a. So at a large distance, the electric field produced is a product of q into a, q into a. Okay, it depends on the product of qa. This suggests the definition of dipole moment, which we have already defined. Okay, dipole moment is defined as, we have last time we have defined this dipole moment of the electric dipole. Okay, which is P is equal to Q into 2A or 2A into Q. It is not a cross product, it is 2A into Q P cap. And we know that direction of dipole moment is from negative to positive charge. Okay, so it is a vector whose magnitude is charge q times the separation between these two charges, that is 2A. Or we can say dipole moment is a product of magnitude of one of the charge multiplied by the distance between the charges. In the direction we have taken minus q to plus q. In terms of dipole moment P if you want to write these equations. Okay, that we had already understood. Okay, so here instead of 2a into q if you want to write, okay, instead of 4qa you can take 2qa separate. Okay, so electric field, in this we can write 2 into 2a into q. So it becomes 2a into q is dipole moment P. So 2 times P upon 4 pi epsilon 0 r cube it becomes. Okay, P cap. Similarly here electric field on the equator we can write as minus P, that is a dipole moment. Vector is shown by this unit vector, so no need to show here. Okay, P, then P cap upon 4 pi epsilon 0 r cube. So electric field of dipole is at very large distance is found to be inversely proportional to the cube of the distance. For a point charge, the electric field is found to be inversely proportional to the square of the distance. This is the main difference between the electric fields produced by the single charge and produced by the electric dipole. In electric dipole, the electric field is inversely proportional to the cube of the distance, while for the single charge, the electric field is inversely proportional to the square of the distance. Okay, so this can be written. These are the two equations which I had already written. Okay, notice the important point that the dipole field at large distance falls off not as 1 upon r square but as 1 upon r cube, that I explained. Electric field is found to be inversely proportional to the cube of the distance. Okay. Further, the magnitude and the direction of the dipole field depends not only on the distance r but also on the angle between the position vector r and the dipole moment. So electric field is depending on the position vector of the point where we are finding the electric field. On the axis, the dipole moment, rather electric field, is in the direction of dipole moment. Okay, and on the equatorial point, the electric field is in the opposite direction of dipole moment. Okay, that we had already studied. Okay, the last time we saw this, that electric field of the dipole on the axis, that is in the direction of the dipole moment, while the electric field on the equatorial point is found to be in the opposite direction of dipole moment. Okay, thank you.